Section 13.5 is over something called colligative properties. Colligative properties, there's 4 of them: boiling point elevation, freezing point depression, osmotic pressure, and vapor pressure reduction. A colligative property is anything that will depend on how much or the amount of the substance that you have in there, not what the substance is. So you could have salt, you could have sugar, you could have whatever. It doesn't matter what the substance is that you're putting into the solvent. All that matters is how much of it you're putting in. The first one we're going to look at is vapor pressure reduction. It does exactly what it says. It will reduce or lower the vapor pressure of the solute or the solvent whenever you put it into solution. So let's take a look at this and see what's happening. If you have a beaker with some water or something in it, the water particles are letting off a gas. We call that vapor pressure. The water particles that are able to use energy to overcome intermolecular forces and turn into a gas. If you take, though, a solute, like salt or something like that, put it in the water, then what happens is it will form attractive forces between itself and the water particles, and it holds some of those water particles in. And so the vapor pressure will actually go down because it's releasing fewer particles. Now this really will only happen, like it says in the notes, with a non-volatile solute, so things like sugars or salt. If you put a volatile solute in there, like an alcohol, then it will actually raise the vapor pressure because it's letting off more vapor than you would expect. The law that governs this is called Raoult's law. This is a formula for Raoult's law that you need to make sure that you know. The vapor pressure of a solution is equal to the mole fraction of the solvent. It's important you note that's a solvent, usually water, multiplied by the normal vapor pressure of the solvent at whatever conditions it is that you're talking about. You can use this equation in all these other colligative property equations that we're going to be looking at to find the molar mass of the solute that you're trying to figure out. So let's take a look at an example of that. In this problem, we have sucrose being added to water. It tells us the initial vapor pressure and the final vapor pressure and asks us to find the molar mass of sucrose. We have 158 grams of sucrose. It gives us the volume of water. It gives us the vapor pressure of the water and the vapor pressure of the solution. And it asks for molar mass of sucrose, and it gives us density of the water at this specific temperature. I'm going to make this really big because otherwise I'm not going to be able to fit all my work in here. We're going to start out by using our vapor pressure equation. We have 2 of these, the regular vapor pressure of the solvent and the vapor pressure of our new solution. So let's go ahead and plug those in. Okay, when we go ahead and plug these numbers in and solve for this, we get the mole fraction of our solvent. Remember, this is the mole fraction of water. The solvent is water here, to be 0.9874, somewhere around there. Now, the mole fraction of your solvent, or the mole fraction of water, is equal to the moles of water that are in this solution divided by the total moles in this solution, which is going to be moles of water plus moles of your sucrose. Now, we don't know moles of sucrose, but what we do know is we know the density of water and the volume of water. If we go ahead and use that density and that volume, we can solve for the mass of water. We get about 641 grams, somewhere around there. Once we have the mass of water, we can divide that by molar mass, which is 18 grams per mole, and we can get the moles of water, which is about 35.65 moles of water. Once we have moles of water, we can plug this back into our mole fraction equation here. In our mole fraction equation, we're trying to solve for here is moles of sucrose. We don't know what that is. If we go ahead and work this on out, do a little algebra, we're going to get somewhere around 0.45 moles of sucrose in this problem. Now in the problem, it gave us the mass of sucrose that we're using, 158 grams, And since we have moles of sucrose, and we know molar mass is grams per mole, we can take grams, divide it by moles, and we get the molar mass of sucrose. Now, when I did this, I got about 347. I think the real answer is about 342. So either I rounded wrong or made a little mistake in my math wrong, or maybe it's supposed to be a little off. I'm not sure. But this is the answer I came up with. All right. Next thing we're going to look at here is what the big deal about this is. Whenever you dump in a soluble ionic compound, it is going to dissociate. And when it dissociates, it causes the formation of a greater number of particles. In other words, guys, if you take something like sugar, C6H12O6 or something like that, and dump it in water, it doesn't dissociate. So for every mole of sugar you're putting in, it only makes a mole of particles. But if you put a mole of a salt in, like NaCl, then it's actually going to make 2 moles of particles. It makes a mole of sodiums, and it makes a mole of chlorides. And so when you put in ionic compounds, it will actually cause double what you would expect of other types of compounds, or triple if you have something that has a formula like CaCl2. That's going to form a calcium, and it's going to form 2 chlorides, so it forms 3 moles of particles. So when you use ionic compounds, you get more bang for your buck. It lowers the vapor pressure even more. The next section talks about non-ideal solutions. If you have 2 volatile solutions, so an alcohol plus water, the vapor pressures actually add together. An ideal solution is one in which Raoult's law is going to be obeyed, or where any colligative property is obeyed completely. There is no solution that is perfectly ideal. Some of them are really close. The ones that are closest to obeying Raoult's law are ones in which your solute and your solvent are very, very much alike, both very nonpolar, both very polar, both very whatever. If you end up with lower than predicted vapor pressures, you expect the vapor pressure to be a certain amount, but it's a little bit lower. The solute and the solvent are pretty similar to each other, and they'll have greater forces of attraction, so they're holding onto each other tighter, and so you'll get a lower vapor pressure as a result. If you are getting a higher vapor pressure than you would expect, that usually occurs because the solute and solvent are very dissimilar, and they have pretty weak forces of attraction. They don't hold on to each other very much, so more of the liquid more of the gas, is escaping. The next thing we're going to look at is boiling point elevation. It does exactly what it says. If you put a solute into a solvent, it elevates or raises the boiling point of the solvent, makes it go higher. This equation right here, this is a really important one to know. It stands for the change in temperature. That means the change in temperature of the boiling point. So it used to boil at 100, now it boils at 101. So the change in temperature would be 1 equals the molar boiling point elevation constant of the solvent. This is a constant. So this is something you either are going to look up in a book or you're going to solve for, multiplied by the molality of the solute in the solution. So the reason why when you add a solute to a solvent it causes the boiling point to raise is because it's doing the same thing as it does with vapor pressure reduction. It's holding those particles in tighter, so it takes more energy to make it start to boil, so it ends up boiling at a higher temperature. So why does adding salt to water? It allows spaghetti to cook faster. A lot of people will say, well, it makes the water boil faster. Not really. It actually makes it take longer to start boiling, but when it starts boiling, it's boiling at a much higher temperature. So instead of boiling at 100 degrees, it's boiling at 105 degrees or 110 degrees. And the spaghetti will cook faster if it's being boiled at a much higher temperature. And then let's take a look at this problem right here. In this problem, we have a solution of an unknown non-volatile electrolyte, that means it's something like a sugar or salt or something like that, is prepared by dissolving 0.25 grams of whatever the substance is into 40 grams of CCl4. The boiling point is 0.357 degrees higher than that of the pure solvent, and we want to find the molar mass. To solve this problem, we can use that equation that we just went over a minute ago. One thing that the problem doesn't have in it that it probably should is it doesn't tell you what Kb is, and you have to know what that is to be able to solve this. I just looked it up in the book. It's 5.02 degrees Celsius per mole. One thing is your change in temperature doesn't have to be in Celsius. It could also be in Kelvin. It doesn't really matter which one you have it in, because it's a change. It's not an exact temperature. Remember, molality is moles of solute over kilograms of solvent. Alright, and so we have moles of solute over 0.04 kilograms of our CCl4. If we go through and solve for this, we end up with our mole value being somewhere around 0.0028 moles of our unknown solute. And since we know the grams of the solute was 0.25 grams, and we know the moles of the solute now, and we know that molar mass is grams per mole, we can just take grams divided by moles, and we get the molar mass of the solute, about 89.3 grams per mole.